The next talk will be via Skype, and the speaker is Paul Wiita, measuring and modeling Blazar variability.
I'll try to keep to that. Okay, let me try and add my screen and start broadcasting. Okay, so good afternoon, everyone. Today I'd like to talk a little bit about the work that I've done with many collaborators over the past few years on measuring and modeling variability in quasars and blazars. Let's see. Just advance to the next slide, please. There we go. Okay, so we have light curves on the ground from optical and radio telescopes taken in a whole bunch of countries, including India, and many of my collaborators on this work are shown in the first couple lines there, and that's not all of them down below. And I think some of this work may have been discussed already at the meeting. What I'd like to concentrate on some of the light curves we've taken from space, particularly those using the Kepler satellite. And then I'd like to shift and talk about models of variability that I've done with several of my students who are listed on the last few rows down below there. And I'd like to focus on work that involves both turbulence within a relativistic jet and the variability produced by oscillations or fluctuations in basically the direction and velocity of flow in the jet. Okay, next slide, please. Thank you. So there we see ground-based Blazar observations. This is some work on data on BLAC collected in 2011 and 2012 in multi-bands. Hopefully you can see the blue, the green for visual, red, and then the black for infrared. It's essentially simultaneous light curves. As you can, I'm sure you all know that most of these blazars can be reasonably microvariable, and on many nights we detect variations of several hundredths of a magnitude and occasionally a couple tenths of a magnitude. The general trend is that these things are bluer when they're brighter. Can I have the next slide, please? So, next, yeah, thank you. And so this shows some optical polarization variations. So the top panel there shows the position angle, which does not vary a lot during the course of these observations. On the second panel shows the percentage of polarization, which goes up to about 30%, which again is fairly strong, but important for blazars. And then the bottom panel shows the total flux. And what you can see is that overall there's a reasonable anti-correlation between the flux that's particularly pronounced in what's labeled segment 2 down below. And so we get the implication that there are at least two emission regions in the case where the more variable one is the less polarized one. Okay, may I have the next slide, please? So now I'd like to shift to a discussion of what we've been able to get from this Kepler space satellite. As you all know, this has been designed to look for exoplanets and has discovered thousands of them by now. And for the first 3 years or so, it was well stabilized and pointing at just one field in the sky, basically in the constellation Cygnus. And we realized that this could also be used. Can I have the next slide, please? So we realized we could also use this to look at a few blazars. Now, it turned out there were not very many, and actually none that were known, because this is an area full of stars, and we don't have too much information about the galaxies behind this chunk of the Milky Way. But there were 4 flat spectrum radio quasars that were just barely within the sensitivity limits of Kepler. But because it's such an extraordinarily sensitive instrument, we were able to get data with basically 1% error, even though we're talking about 18th magnitude objects. So the data is only dumped basically once a quarter or once a month, but then it shifts from one chip to another on the CCD camera. The tremendous advantage that Kepler has over any ground-based monitoring is that you get data sets that functionally lasted for about 3 years, and we can get the data pushed down every 30 minutes. We did get some short cadence 1-minute data, but because the noise in that was too much, so we discontinued getting that and just worked with 30-minute data. Can I have the next slide, please? So you probably can't read much from this, but basically it just says we have 4 objects between about 18th and 18th and a half magnitudes. The redshifts range from about 0.5 to 1.5. And we thought they were all flat spectrum, but it turned out with better measurements, one of them was actually somewhat of a steep spectrum radio galaxies. So probably, probably not a blazar. And so what's shown in the next slide are the light curves for 2 of the objects. And you can see each quarter is shown there. And you can see for object B on the bottom, we're missing data every 4th quarter because the object fell on a bad chip within within the Kepler camera. On the top, you can see that there looks to be lots of small-scale variation, but much of that is noise, and a lot of the long-term changes within each quarter are actually instrumental drift. So we had to try to take those out, and that was rather tricky. This next slide shows the same light curves for the 3rd and 4th object. And then we did some corrections on the small scale, taking out some of the long-term drift that was due to the velocity aberration of the moving satellite. We did some massaging to fill in the 1-day gaps when the data was lost and to take care of the glitches that are produced as the satellite swings around to dump its data, and thermal the differences in temperature on opposite sides of the satellite cause a temporary change in the sensitivity of the camera. And so if you see the next slide, this is showing a reasonably large flare early in this quarter, about 8% or so. And then you see 2 of the glitches further on that are just due to this rotation of the spacecraft as it sends its data. So we modeled those and took those glitches out, as you can see on the light curve on the bottom there. So let's go to the next slide, please. And so the next slide just shows one of the power spectra for 1 quarter of one of the objects. And so we get a slope in the low frequency end of about minus 1.8 for this quarter, and it shifts over to white noise at the high frequency end, which is basically instrumental. So after we looked at all of the quarters individually, we then went to stitch them together. That allows us to look for any longer term variations. But we have multiplicative and additive offsets in the signals, which we think we've taken into account reasonably well. Now, next slide. And so what's shown over here are the before and after for 2 of our objects, where you see the substantial jumps as you go from chip to chip. And then we can take most of that out and leave predominantly real signal left behind. And so what's shown in the next slide are the overall power spectra, where we combined all of our data for 13 quarters. And we can see some very nice results with power spectra that range between about minus 1.6 and about 1.7 is our best estimate for the power spectra for these objects. There's a slide here, but I'm going to skip that. It doesn't give much more useful information. So I just go to our conclusions in the next slide. From Kepler, we have really good photometry done at tremendously excellent sampling. We've got data basically every 30 minutes for nearly 3 years. We've got nice quasar power spectra that basically agree with optical observations and the X-ray observations of Seyfert's, that the majority of these power spectra between about minus 1.7 and about minus 2.2 when you look in the literature. So we think we're appropriately combining the data sets from different quarters. While we were hoping we might see some periodicity or quasi-periodicity, that's extremely rare among blazars, and so we did not see that. And unfortunately, only one of our objects was, as not even as active as a typical blazar, but at least was reasonably variable. The others didn't show us any large flares at all. So when continuing this work, if we look at the next slide, We've been analyzing additional targets now that Kepler is in the K2 mission, where it can no longer point for a very long time and has to be moved from one field to another basically every quarter. So we've gathered data on a couple of objects per field, and we hope to continue to analyze that data as long as Kepler stays alive. Okay, so now let me turn to modeling variability, which is on the next slide. This is some work that I've done with one of my students, Victoria Caliphate. We used a relativistic turbulence spectrum and compared that with the standard Kolmogorov spectrum. We assumed that that we had a large cell that might be as big as the radius of a jet or a fraction of the radius of a jet, and then went down multiple layers of fluctuations where we would determine the velocity in each cell as a function of its size. And we see the output of that in the top image. We have a bulk velocity of 0.99 c, a maximum turbulent velocity of 0.3 c, and it's being viewed at different angles just to show you the tremendous enhancement in flux and variability that you would see if you were looking straight down the Blazar jet, as opposed to the 3-degree angle at the top and 10-degree angle in the red, and then you can barely see a blue line at the bottom if you were looking at that thing at 30-degree angle. The bottom panel shows the same bulk velocity in a fixed angle this time, but changing the maximum turbulent velocity from 0.9 c down to 0.1 c. And what we realize from looking at these things is whenever we have a turbulent velocity that's more than about 0.6 c, we get light curves that look nothing like any Blazar that I've ever seen. That may not be too surprising because that would correspond to supersonic turbulence in the jet, which would correspond basically to speed of light over the square root of 3. But for turbulent velocities of up to about 0.3 c, the light curves have general shapes that are pretty acceptable. So we can get power spectra of these, and what's shown on the next slide then are these power spectra, and we get them basically having red noise and slopes that are shown on the left between minus 2.1 and minus 2.05 for 2 different cases. And so that's reasonable. We like that, but the difficulty is that we basically can only get a couple of decades in frequency. So what we then next did was somewhat more interesting. We can look on the next slide. And what we've done is model propagating jets using the Athena relativistic MHD code that's mostly been developed by Jim Stone and his colleagues at Princeton. And we injected a relativistic jet into a constant density medium. And this is work that I've done with a couple of other students, Max Pollock and David Pauls. And we've done simulations where the jet density, it ranges from about 1,000 to about 1/10 of the ambient medium density. And they're all relativistic jets with bulk velocities between 0.9 and 0.998 c. So what's shown below is a simulation at a certain stage of densities on a logarithmic scale. So you can see the jet propagating from left to right, and it's gone unstable at this point and starting to wiggle around. You see the highest density is the yellow bow shock here, and the green outside is the ambient medium through which the jet is propagating. So I'll show you a few more of these images on the next slide. So these are, again, at different relativistic speeds. You can see the jet on the right has a relatively high density and a relatively high velocity, and it stays quite stable and it plows through, but the inner green area there corresponds to the cocoon of the jet. And so let me now show you one more of these images of a quite stable jet, which with parameters that look quite reasonable. And what we've done then is analyze the fluctuations in the flows and computed the velocity variability due to the differing Doppler effects from a region on this, which, let's see, basically behind the first reconfinement shock. So it's a little hard to see probably on the image, but if you look about 1/7 of the way from the left in the jet, there's a more intense yellow region, and that's where the jet is being recombined for the first time. And that's an area from which the intensity would be particularly high. There'd be also great intensity from the bow shock at the front, well, the Mach disk shock near the terminus of the jet. And I wish I had a pointer that I could show these features to you, but we'll have to live without that. But that region should not be anything near as variable as the fluctuations from the inner portions of the jet. And so the next slide shows at the top one of the turbulent light curves that I discussed earlier, and at the bottom, one of the light curves we get from looking at the fluctuations of basically the Doppler boosting of the emission from that inner jet region. And then when the next slide shows the power spectra. And the very nice thing about this is that the blue portions of the curves at the lower frequencies correspond to the variability that we see from the bulk velocity variations and the changes in the Doppler shift. And then the yellow ones off to the right at the higher frequencies correspond to the turbulence. And we can match these up pretty well. The slopes are sometimes quite consistent, and sometimes the turbulent power spectra are a little bit flatter than the bulk power spectra. But overall, what we've done here is get 5 decades of variability in a reasonable way, which is longer than we've observed any of these objects, in a sense, going from days up to decades. So I think we can arguably take a look at the next slide. This gives the conclusions from the modeling. That turbulence behind strong jet shocks is expected. So we've inserted that into our models. We can get good turbulence spectra and pretty good parameters, reasonable jet parameters, give us light curves and power spectra that look reasonably like observations and could well play a good piece in the variability we see over the shorter time scales. But because the jet is fluctuating, the changes in the direction or the speed of that bulk velocity obviously can give us substantial observed variations, and those typically would take longer time scales for us to see them. So you might think of the turbulence as providing most of the fluctuations on time scales of days and weeks, and then the bulk velocity changes perhaps on months to decades. So overall, they give us nice fits, or at least reasonable fits, to both light curves and power spectra over these very long range in times. I like to end with a couple of movies, so I hope those can be projected over there. So let's see. If you click on that, I don't think you're not mirroring my screen, so hopefully a movie will go. Can you make that happen? Okay. So now we're seeing the jet propagate across. So this is a relatively fast jet with low density, and I'll make that go again. And so you see it moving across the screen, the bow shock moving out, and then we terminate the computation when the jet has propagated all the way across. And we'll show you another movie. The next slide shows us a somewhat lower velocity jet and a somewhat higher density. And this jet then goes unstable relatively early. So you can see that propagating across, but instabilities grow, break it up. And so fundamentally, those more powerful jets, one makes good simulations of the morphologies of an FR2 radio galaxy. And here we see good morphological similarity to many FR1 radio galaxies. So I'll just replay this one more time. And that's all. Thank you very much.
Thank you, Paul.
Can I get questions?
Running behind schedule.
Okay. I'm sorry if I was wrong. I didn't have a clock with me. So.
One question I could relay to you. Yes, is there?
In the Kepler data, is that optical emission from disk or the jet? Is that known?
Yeah, in the Kepler data, is the emission from the disk or from the jet? That's the question.
Yeah, well, for the flat spectrum objects, it's almost certainly predominantly from the jet. One of the objects was a steeper spectrum, and so the probability that more of the emission was from the disk can't be ruled out. But we don't have really good spectra of these objects. They all were flats, they were all quasars, so we had emission lines from them. But our hypothesis was most of the emission was coming from the jet. And for at least one of the objects, I think we're convinced of that. But for the others, it's not absolutely clear.
So let's thank Paul again.